Now let's practice doing some calculations. Remember that S is a vector, and this is related to SL and SR in this form. Yeah. Now, because S plus and S minus are uncorrelated, their joint probability distribution factorizes into the marginal distributions of each component S plus and S minus. And we know that each component follows a Gaussian distribution since the whole joint probability distribution is Gaussian. That's our assumption to start with. And given this relationship, which comes from that, and given that the signal powers are like that, then we plug this in, this over that, we can get for the plus, S plus, and get for the S minus, and you can calculate that this is the result. Okay, now given this result, you plug these into the original form, and you will go back to this probability distribution, okay, because the multiplication of two exponential is exponential of the arguments inside. I add it together. Okay. Well, the same vector can also be expressed in the old coordinate component SL and SR, for which we know that we have assumed that it follows a Gaussian distribution, and if we know its correlation matrix, we can write the Gaussian distribution in this form by taking the inverse of this correlation matrix. Now let's expand this term out for two components, SL, SR, put this in, and that's the detail. It's a joint probability distribution for each of the four terms, LL, RR, LR, RL. Now, because these all refer to the same probability distribution, no matter whether S is in terms of S plus S minus or in terms of SL, SR, they for the same probability density, they should be exactly the same since the two vectors are really related to each other only by coordinate transform. They should not change the density. So therefore, the argument of this exponential and here, they should be exactly the same. And you can try as an exercise to verify this by work it out. We can calculate the summation of signal power, so S plus square plus S minus square. Okay, just plug these formula in, you find out it's equal to SL square plus SR square. So the summation of power in the new coordinate system is the same as the summation of power in the old coordinate system, and this is just a property of coordinate rotation. You can also have the noises in the left and right eyes. When you sum and subtract on each other, you can get its coordinate rotated form, n plus and n minus, analogously just as in a signal. And let's see, we can calculate its variance, plug this value in, and the variance would just be equal to this input variances. And if the input variances are the same, and then it's equal to n squared, so the variance of n plus is still the same as the original variance in each of the independent identically distributed channels. Okay, and similarly, we can see its correlation. Indeed, correlation comes out this term equal to that term, they both equal to n squared. Remember, each is equal to n squared, so they cancel out equal to 0. So indeed, they are not correlated. And so n plus n minus are also independent of each other and identically distributed Gaussian noises, just like NL and NR. Okay. Now, if we take the output as the summation of the signal and noise, whether it's in the original left and right eyes, then in the rotated form, O plus and O minus is also equal to corresponding signal and corresponding noise. And let's recall that then their variances will be equal to the signal variance plus noise variance, just as a property of Gaussian variables, also in the rotated form O plus and O minus. And we can verify O plus and O minus they are indeed uncorrelated just by writing its form out and calculate the correlations. So S plus, S minus come out this way. N plus and N minus, we know it's uncorrelated 0. Signal and noises are not correlated, so you only have the signal correlation. And we know S plus and S minus are not correlated, so it's equal to 0. So therefore, O plus and O minus are not correlated. Because O plus and O minus are uncorrelated, the joint probability distribution also factorizes into the probability of the components. Let's recall that the mutual information between output O and input S, when the output is simply the input signal plus noise, the mutual information depends only on the signal to noise in this form. And this is the mutual information between O plus and S plus, or between O minus and S minus. It's the same. And we have a similar form of mutual information between OL and SL, OR and SR, as long as O is always equal to the signal S plus noise N. Now, because O plus and O minus are not correlated, so there's no redundancy in terms of the information carried in them. So the total mutual information between the vector S and the vector O is simply the summation of the mutual information in a component, in the plus component and the minus component. However, because SL and SR, left and right eye input, they are correlated, and so should be the OL and OR. And so therefore, this mutual information and that mutual information, there is redundancy between them, and so therefore they add together should be more than the total mutual information due to the information redundancy. Let's see using an example. Let's say that input signal to noise in the original left and right eyes is 10. And the correlation coefficient R between the left and right eyes is R in here, yeah? This R is 0.9, so it's very correlated. Then we can just plug in to calculate this, yeah, O plus S plus or O minus S minus for each of these terms, just plug in the values, okay, using these values to plug in. And then we find it's 2.16 bits for the plus summation channel and 0.5 bits for the difference channel. And you put these into that 2.16 and 0.5 added together. This added together is 2.66 bits. However, we can do the same calculation between the left eye input, output and input, and right eye output and input, and do the same calculation. Put that in using these values. It's 1.73 bits each channel. Put this into that, you add them together, that's 3.46 bits, and this is a bigger value than that. Now you can just calculate how much is the redundancy in the original output channels OL and OR. It's this way. And of course, there is no redundancy in the O plus and O minus coordinate system.